Max area of an island. Let's see. You're given a m by n binary grid, a matrix grid. An island is a group of ones representing land connected four directionally, horizontal or vertically. You may assume all four edges of the grid are surrounded by water. So the area of an island is the number of cells and a value 1 in the island. Return the maximum area of an island in the grid. If there's no island, return 0. So how that kind of works is that you have a bunch of zeros here, which are water, and then you have ones, which represent land, and you want to return the maximum island, the largest island, with the most amount of ones connected to each other, either horizontally or vertically connected to each other. So this is like a clustering type of examination. So you want to find the maximum cluster in a grid. So for instance, this one would be this one, 1, 2, 3, 4, 5, 6, just by inspection there. So in order to approach this question, I think it would be best to use, there's two ways of doing this, or multiple ways of doing this. But the first one I kind of jumped in my mind would be a depth first search. Let's look at the constraints here. You have the grid length. Yeah, this is the, I believe, the row, and n is the column. And you have, obviously, you have a minimum of at least how much, and the grid's either a 1 or a 0. Great, let's use Python to figure this out. So we have a depth first search. So we want to know the area of each shape connected to the grid, and we want to take the maximum of these. Let's see, if we're on an island, on a land, and we want to explore, I guess, every square connected to it if it's a 1. So we'll try to do this probably recursively. There's an iterative solution too as well. So we gotta also make sure that we don't count the squares more than once as well. So let's see if we could make this work. Let's see. We need a variable to store the maximum number. So let's just say max equals 0. There, we initialize it, and let's kind of cycle through the range of the, I guess, the y direction, you would say. So for I in range, let's see, the length of the grid, that's what we want, the entire length of the grid. So it's going to be a nested for loop, because every time we do, what's happening? Oh, I see. So every time we do a cycle through the y direction, we need to do the same thing. I mean, through the x direction, we need to do the same thing through the y direction for j in range. Length of grid, there you go. And every time we go through this, so each individual, oh, we need to do this in the columns, I should say. And we need to, let's see, if the grid that we're on, I, j, there you go, is equal to 1, then what we want to do is that we want to find the, what am I doing here? We want to find the max, we want to find the maximum between max, and we're going to do a depth first search, probably either recursively. So we're going to do, let's just make a new function here, which takes in the grid and the I and j directions as well. And then we want to return the maximum number. That's what we're looking for. Max. There you go. So we have a kind of a skeleton going there, and this is basically our solution. Now we need to get this depth first search algorithm working properly. So depth first search is a standard way of searching through, I guess, a binary matrix, and you want to be able to look at each route that you're taking and make sure that you're keeping track of where you go and where you want to be, and then traversing through a graph essentially. Let's kind of make it here. DFS it. And then we take in the grid, we take in I, then we take in our j. And what we want to do is that we want to There's different ways of doing this, but I think establishing the constraints is a little bit easier. So let's just say that we can't go outside our grid, essentially. So if I is less than 0, right? So we don't want to go too far to the left of the grid. We won't go beyond the bounds of the left of the grid. Or I is less than the greater than equal to the grid length of the grid. So you want to go too far to the right. What am I doing? Length. And then or if we don't want to go too high, too above the grid, let's say, and we don't want it to go too low as well, so below the grid. These are the boundaries. Let's see, what am I doing? The length of the grid. Right there. High. Then, or we don't want to go. Another one people forget is the if we're on actually the one we're on already. We don't want to count it if it's 0. Let's see, I j equals 0. There you go. So if we don't go too far left of our grid, we don't want to go too far right of the grid, we don't go too above our grid, and we don't want to go below our grid, and we don't want the number we're on, the tile we're on as well, to be equal to 0. See, these are the constraints we need. At least that's how I kind of take it. I mean, you could break that up to smaller parts and then do it individually and then calculate the DSF for it later. But if we're on any of these, let's return 0 because we don't need any information from there. Next, we want to do is initialize our grid that we're on to 0 because every time we go on a grid, on a tile, I should say, we want to make that equal to 0 because we don't want to double count it or count it again. So once we're on a tile that's not within our constraint, that means our count is incremented by 1. There you go. And then now we want to run a depth first search recursively using going basically looking above the tile we're on, below, left, and right. So because remember right here, it's 4 directionally, right? So we want to make sure we're looking at tiles top, bottom, and right if we're on this tile specifically. Let's kind of break it down like this. So let's see, count is equal to depth first search of the grid. So basically this is pretty straightforward. You just kind of look at it like this, plus 1, because you want to look 1 above the I direction. And then you want to do count plus equals this stuff again, looking for the grid. Looking at, let's see, I minus 1, because you want to look at below the tile that you're on. You want to, now you're looking for left and right, basically. Let's see, grid I, comma, j plus 1, and then count, oh my gosh, plus dfs, grid I, j minus 1. Everything looks kind of good so far. Oh yeah, forgot to return count right here. There you go. So we go through the y direction and the x direction, the y direction for each tile we're on is equal to 1. We're gonna run this DFS algorithm where we will stay within our bounds. And obviously, if we're on tile 1, make it equal to 0 because we don't want to count that again. And if we're on a tile that's equal to 1, we want to increment count by 1. And then we search north, south, east, and west. And if they have a tile, then we add to the count. And then we take the max of that. And then with the max we have already, then we return that. So that should work. Let's just, oh, what am I doing? Count plus minus, oh, whoops. What am I doing? I forgot to, what am I doing? I don't need to increment 1 there. It's already equal to 1. Let's see. Awesome, that works. Let's submit it. Accepted. Awesome. Let's see. Time complexity is big O of row times column because we're searching through this row. And each time we're doing that, we do column. So R times C will be the time complexity. So of the given grid, so we count each square at least once. That's good. Space complexity would also be our row times column, because we keep track of each tile we're on. So we take this max here, increment 1, so we don't really need to keep anything else afterwards. So yeah, row times column as well. And that's it.